Recording. There we go. Sorry, I forgot to record earlier. We just got through that. Okay, there we go. Okay, so now we have H2PO4, and what is the charge? Minus. And when we have HCO3, it becomes H2CO3, and what is the charge? Nothing. What do we call the two of these together? I don't remember if they covered that. The two together are called a conjugate acid-base pair. So any pair, again, the two together are called a conjugate acid-base pair. Yes, any of those pairs. So when we go to, I wonder if I have a definition of this somewhere. That would be super clever. No, I don't. So I'm going to actually write it down right now. We'll probably come across it later. A conjugate acid-base pair, if you have to define it, it is a pair of chemical species that differ by a single proton, H+. Does that make sense? Because you're either adding one on to get the conjugate acid, or you're taking one off to get the conjugate base. So let's just toss that up here. I'm sure I have it later on, but that's okay. A pair of chemical species that differ by a single proton, H+. So anytime I ask you for a conjugate acid-base pair, those two chemicals should look almost identical. There should just be one extra H on one of them and one less H on the other, okay? Good, can I move? Nobody's saying no, okay. So in the examples above, can you see any substances which could act as both acids and bases? Like if we look, is there anything that appears in an acid column that also appears in a base column? Yeah, we have HPO4, right? We've got HPO4 here. Oh, yeah, it's in the base, but it is also in the acid, yes? Is there anyone else on there who is doing that same sort of thing? HCO3. HCO3 is hanging out as a base, but it can also act as an acid. So we have HPO4 minus and HCO3 minus. And how do we spell that word when we have a substance that can act as either an acid or a base? See if you can spell it. Remember amphi, like amphibian, because amphibians can live on both the water and the land, right? So amphi, and then protic, it can do both things with protons. It can both donate them and it can accept them, just like a frog can live on both water and land. Did you guys like the picture of the frog? Please tell me you like the picture of the frog. I actually spent a fair amount of time, ridiculous amount of time, getting that picture of the frog. Like, so he was on land and then he was swimming. Anyway, okay. All right, another definition of amphiprotic is a substance which can act both as a what donor and a what acceptor? Proton donor and a proton acceptor. So those are both good definitions for amphiprotic. Amphiprotic. Did you guys know that Connecticut has 2 T's? No, is it the T's? No, the C's. It's got 3 C's. It's got 3 C's in it. Connecticut. It's Connecticut. I'm 50 years old. I did not know that till this year. Holy mackerel. I was like jaw to the floor. Anyway. Now, how are you going to know that a substance is amphiprotic just by looking at it? Well, you have to have a hydrogen, because if you don't have a hydrogen, there's no hydrogen to donate, yes? If you are amphiprotic, you must have a negative charge, because that's going to allow you to accept the positive H+. However, there is an exception to this, because water is kind of funny. Water does not have the negative charge, but it is amphiprotic. You are not going to come across any other neutral amphiprotic substances, okay? Water is it. Otherwise, if you're going to be amphiprotic, you need a hydrogen and you need a negative charge, okay? Now, in order for an acid to act as an acid, there must be another chemical willing to act as a base, just like you could not have oxidation without reduction, yes? And just like we had, things which had a higher oxidation potential and a lower oxidation potential, we have acids which are better at losing their protons and acids which are not as good at giving away their protons, yes? And on your data booklet in page 6, there is a table, okay? And we have some annotations on here. So the gray area at the top of the table, that is where you find your strong acids, okay? And if I could print this out for you in color, I would, because like the red is for acid, right? And the blue is for base, and then the yellow is for I don't do either of those things, yes? So if we look, our acids are on the left, our bases are on the right. Just like your oxidizing agents were on the left and your reducing agents were on the right. It's very, very analogous, okay? If we are in the gray zone, those substances are what kind of acids? Strong. And what do strong acids do? They give away their protons, and then what? Do they ever take them back? No. So if I am HCl, and if this is my proton, so I am Cl minus, and this is H plus, I give away my proton. Who's feeling active today? Nicole. Okay. So if I give away my proton, try and give it back to me. I'm now fluoride. Try and give it back to me. Oh. No. And in fact, it's not even like that. It's that as a base, because I would now be a base, right? Because I was an acid, now I am a base. I should be trying to take this proton. Now, I'm going to try and take this away from her. No success, yes? Because as a base, thank you so much, Nicole. As a base, as the conjugate base of a strong acid, I am too weak to behave as a base. I am unable to take a proton from anybody, yes? And that is why our arrows all go one way, right? So even though chlorine, for example, who I just was, like I gave away my proton and it became chloride, even though it's in the base column, it is too weak to act as a base. They cannot accept protons. So the conjugate bases of weak acids, or sorry, the conjugate bases of strong acids cannot act as bases. Now, as we go down, as we get out of the strong acids, we get into the weak acids. Okay, so everything in that sort of pinkish shade on this table, okay, all the way down to that bottom gray zone, those are weak acids. Everything in there is a weak acid. But we have our stronger weak acids at the top, and we have our weaker weak acids at the bottom. Yes? And if we look on our table and look for the labeling, you can see we have weak here. So those are the weakest of the weak acids are down at the bottom. And the strongest, of the weak acids are kind of up at the top here. Okay, and then we get into actual strong, right? And what that means is that, say, iodic acid is better at giving away protons than, right, iodic acid here is better at giving away protons than nitrous acid. Okay. Now, the stronger you are as an acid, how does that affect the strength of your conjugate base as a base? If you have a conjugate acid that is stronger but still weak, its conjugate weak base will be a weaker weak base. So they go like this, right? The stronger you are, just like oxidizing agents and reducing agents, the stronger oxidizing agent you are, the weaker you will be once you have lost your protons. You will not be a good reducing agent. Yes? Okay. So we have along here, you can see strength, our weak bases are up here, the weaker weak bases. And then we work our way all the way up to the stronger weak bases down to the bottom. You can see, what is our strongest weak base? OH minus, yes? Okay, OH minus is our strongest weak base. And then finally we get to the gray zone at the very bottom, and those are our two strong bases, okay? These are our only two Bronsted-Lowry strong bases. These two right here. Are there any other substances which are strong bases but are maybe not Bronsted-Lowry bases? What's the other definition of acids and bases? There's Bronsted-Lowry acids and bases. And a Bronsted-Lowry is a proton donor. Bronsted-Lowry acid is a proton donor. Bronsted-Lowry base is a proton acceptor. What is the other definition of acids and bases? Starts with an A. Arrhenius. Yes? Arrhenius. And it's spelled Arrhenius, but pronounced Arrhenius. And what do Arrhenius acids do? They're not proton donors. What do they release? H plus in solution. Okay? So if we were to compare the two, if I had HCl, it dissociates, yes? But if I have Bronsted-Lowry, that's not good enough, yes? Because a proton donor also needs a proton acceptor. So we would have HCl plus, if there's nothing else around, H2O will always work, okay? Goes to, now, what do we end up with here? H3O plus and Cl minus. Yes? Did you learn the name of this ion? That is the hydronium ion. So this is reality. This is shorthand. Okay? In reality, hydrogens don't just float around by themselves in the water. They attach themselves to water molecules and become hydronium. Okay? Sometimes you will come across the question, what is the strongest acid that can exist in water? And the key to that question is going to be that can exist part. Because if I put HCl into water, does HCl exist in the water? No, right? Because this is all gone. What does it turn into? H3O plus. So the hydronium ion is actually the strongest acid that can exist in water. Okay? So any acid that is stronger than hydronium gives away its proton and ceases to exist in water. Yes? It's a bit of a semantics game. Do you know what I mean? Like, it's not a huge important concept or anything like that, but if you go back to our data book, let's say, and we go to page 6 and we look, who is the strongest of the weak acids? Hydronium. Yes? Because anytime you have one of these strong acids, they will give their protons away to water, and all you'll be left with is hydronium. What's the strongest base that can exist in water? Oh. Well, if we look once again at an Arrhenius base versus a Bronsted-Lowry base, first of all, our Bronsted-Lowry base, what is the definition of a Bronsted-Lowry base? A proton acceptor. What's the definition of Arrhenius base? An Arrhenius acid was a substance that releases H+ in solution. What is an Arrhenius base? That is a Bronsted-Lowry base. It's something that releases, so that the Arrhenius all has to do with something being released. Okay, so Arrhenius, you're either releasing hydrogen if you're an acid, or you're releasing hydroxide. Okay, can you guys think of an example of a substance that releases hydroxide in solution? KOH, NaOH. Those do not meet the definition of a Bronsted-Lowry base. They are not accepting protons. They are simply, that NaOH crystal or that KOH crystal is simply dissociating, okay? So Bronsted-Lowry acids all also qualify as Arrhenius acids, and vice versa. All Arrhenius acids also qualify as Bronsted-Lowry acids. But with bases, and this is why they had to come up with a different definition really, is that you can't give this one as an example for a Bronsted-Lowry base. You could, I suppose, say hydroxide plus H2O gives H2O plus hydroxide. Yeah? Where you have a hydrogen moving from here to here. Yes, and that does happen, but it's kind of goofy. Yeah? So we don't usually talk about that, but what we would talk about is something like NH2 minus plus H2O, and it becomes NH3, and we are left with OH minus. So both of them end up producing hydroxide ions, but the Arrhenius base does it simply by releasing them, and the Bronsted-Lowry base does it by taking a hydrogen away from water. Yes? That's the difference. You're not going to be called upon to like define those, possibly in regular chem, but not on the AP exam, I don't think. Probably not. Maybe Bronsted-Lowry, not Arrhenius. Okay? So who is the strongest base that can exist in water? OH minus, because once you've got, this one is a stronger base, right? This is a strong base. It cannot exist in water. It accepts a proton, and we're left with hydroxide, which is the strongest base. So who is the strongest base? It is OH minus. So the strongest acid is H3O plus. The strongest base is OH minus, but those are only the ones that can exist in water. You can have stronger ones, but they immediately react with the water. Okay, can I go back to the other pitch? Oh, there we go. Okay. So going down to the bottom part of the table, just noting that the conjugate acids of weak bases, or sorry, the conjugate acids of strong bases, right? These are our strong bases. What can we say about their conjugate acids? They're not just weak bases, they're not just weak acids, they are too weak to actually act as acids. They cannot donate protons. One of the things that I often come across is because you've got that gray zone at the bottom, and we know that is where strong bases live, yes? I often get people thinking ammonia is a strong base because it is down in that section. Here's ammonia here. Is ammonia a strong base? No, because when it is there, it is on the acid side of the table. What we're saying is it's not a strong base. It is the weakest acid we could have. It's so weak it can't even accept a proton. It cannot act as an acid. Ammonia, and in fact I put it on here, ammonia is a weak base. I will say that a lot because people always seem to forget. They seem to think, oh, look, it's a weak acid because it's on the weak acid side, but it's too weak to act as an acid. It's a strong base because it's down in the gray section, but it's on the wrong side of the table. Okay, so just remember all of that. Ammonia is a weak base. And we also have K values for these. And what is a K value? K in general is concentration of what over what? Products over reactants. And so if we have a Ka value, that's going to be the concentration of the dissociated stuff, right? H plus times A minus over HA. Yes? And so the stronger an acid is, the more dissociated it is. And so by that same token then, if it is more dissociated, then this number here is going to be larger and the number on the bottom is going to be smaller. Yes? Okie dokie. Top 6 acids are the strong acids. Their conjugate bases are too weak. We just talked about that. The bottom 2 bases are the strong bases. Their conjugate acids are too weak to let go of their protons. So there we go. The remaining acids all set up an equilibrium with water. They do not completely ionize. Here is a question for you. Is Hso4 amphiprotic? Hso4. So let's think about these two equations here. Hso4 releasing a proton or donating a proton. Is that okay? Does that happen? Well, let's go to our data booklet once again. There we go. And if we go to Hso4, Can Hso4 act as an acid? This is not a hard question. Yes, yes, it can. Okay, it's right there in the middle-ish section of the weak acids. Yes. Can Hso4 act as a base? And the answer to that one is no. Okay, it is that, you know how water is the one exception where it's amphiprotic but it's not negative? Yeah, this is the one exception where you've got the H plus, you've got the H, you've got a negative sign, but it's not amphiprotic. And the reason it's not amphiprotic is because H2SO4 is a strong acid, and so its conjugate base is too weak to accept a proton, so it cannot act as a base. So HSO4 is the only thing with an H and a plus, or sorry, an H and a minus that is not amphiprotic. Why does it keep going back to the beginning for me? Okay. And I think it basically says that there. Equilibrium 1 does occur. Equilibrium 2 does not occur because H2SO4 is a strong acid. And so HSO4 absolutely sucks at accepting protons. Okay, it is an incredibly weak base. It will not act as a base at all, so it is not amphiprotic. So in order for a substance to act as an acid, it must be mixed with a base, a chemical capable of accepting a proton. And if we have something other than water present, then we can have these two things react here. So an amphiprotic substance can only donate a proton if it is mixed with something that can accept the proton. That would include water, okay? But if we put it with PO4 minus, HCO3, we've got that hydrogen, we've got the negative sign, so we know that it is amphiprotic. What is it going to act as when it reacts with the phosphate ion? It's going to act as an acid. It has no choice, right? Phosphate doesn't have a hydrogen to give it. So this is going to be our Bronsted-Lowry acid. And this is going to be our Bronsted-Lowry base. Who are the products of that reaction there? CO3, 2 minus plus HPO4, 2 minus. Yes. Now, because this is an equilibrium, we will get it going backwards as well. So in the reverse reaction, who is the Bronsted-Lowry acid in the reverse reaction? HPO4 is the Bronsted-Lowry acid in the reverse reaction, and CO3 is the Bronsted-Lowry base in the reverse reaction. Could you identify a conjugate acid-base pair in that reaction? Oh, look, it says label the Bronsted-Lowry acids and bases and identify the conjugate pairs. So we're gonna identify the conjugate pairs by going like this. We're gonna attach one member of the conjugate pair to the other with a little bracket like that, and we'll attach the other one with a little bracket like that, okay? Something like that. Who would I attach HCO3 to? Who is its conjugate pair? CO3, 2 minus. That is a conjugate acid-base pair. Conj for conjugate, AB for acid-base pair. Who is our other conjugate acid-base pair? Has to be the other two, yes? The two that differ by 1 proton only. So the HCO3 ion in this case is acting as an acid because the PO4 minus is a base capable of, what does the base do it? Accepts or gains a proton. Capable of accepting a proton. Okay, excellent. Now, this is where we get into the meat of this. All the rest of it prior to this is mostly just definitions and stuff, yes? When we take a weak acid and we mix it with a weak base, we get an equilibrium set up between the two, and we can determine whether the reactants are favored or whether the products are favored based on the strength of the acids. Do you remember in electrochemistry when we said either the reaction will go or it will not go? Yes? Acids and bases is not quite as cut and dried. It's not just go or not go, but it is reactant favored or product favored. Yes? So if we look at this and we have this reaction here, HCN plus F minus, who are the products of that reaction? HF and CN minus. If I had to attach HCN to its conjugate pair, who would I attach it to? HCN would attach to CN minus, that is a conjugate pair. Who is our other conjugate pair? Well, we got nothing left except for these two, yes? That is our conjugate pair. So in our reactants, who is the acid in the reactants? HCN is the acid, and in the products, HF is the acid. That means this is the base, and this is the base. Are any of those substances strong? Are any of those things a strong acid or a strong base? No, they are all weak. If you want to double check, we can go and look at our data booklet. We have HF and HCN. Here's HF, it's a weak acid. F minus, its conjugate base, is a weak base. CN, it's a little lower down, I think. Where are you? There you are. HCN and CN minus, they're all weak. Yes, weak acid, weak base, weak acid, weak base. Now, out of our two acids, who is the stronger of the two weak acids? HF, because it is higher up on the table, yes? So HF is the stronger of the two weak acids. Back to the beginning again. Okay, here we go. So HF was stronger and HCN was weaker. Without going back to the table, can you tell me which is the stronger of the two bases? CN, because the stronger the conjugate acid, the weaker the conjugate base, and vice versa. So the weaker acid has the stronger conjugate base. So think back to your electrochem. And if your stronger oxidizing and reducing agent were in the products, would that be a go situation or a no-go situation? If your stronger things were in your products, would that be go or no-go? If these guys are stronger, it means they are better at doing their job. HF is better at giving away protons. And CN minus is better at taking protons. Should have left myself more room there. So where are we going to end up? Does someone want to be CN minus? It's fun. Wasn't it fun, Nicole? It was fun. You enjoyed yourself, even though you're like, oh my God, this is so awkward. Who wants to have fun? Harry, you want to have fun, don't you? No. He's like, no thanks. That look, just I'm like, he's not doing it no matter what. Okay, gotcha. Okay. Yes. Oh, yeah. Okay. So you're going to be CN minus. Okay. So you are the stronger base. Okay. So you're the stronger base. He's better at accepting protons than I am, but I don't have my proton. Yes. Okay. There you go. But because you are weak, and I am weak, I do get it some of the time, but immediately, oh, yes? So where are we spending most of our time? With you, in his acid form. He's the weaker acid, right? Try giving that to me. No. Okay, fine. Yes. Not as much fun as running around the room, but you know. So does it make sense that they will spend more time in their weaker form? Okay, because the stronger things are better at stopping being themselves. The strongest acids never get to be acids anymore as soon as they have something to react with. Yes, they just give away their protons and they're no longer acid at all, ever again. Yes? So this is just going into the Ka, so the Ka of HF is larger than the Ka of HCN, so HF is the stronger acid. A stronger acid, is it better or worse at giving away its protons? Better. And since the stronger acid, which is HF, gives away its proton in the which reaction? Reverse. Yes, that's right, reverse reaction. That means the reverse reaction is favored, and therefore who is favored, reactants or products? Reactants. So is the KEQ of this acid-base equilibrium going to be large or small? It's going to be small because our reactant concentration is big and our product concentration is small. So that's going to be small, which is i.e. less than 1. Since the reactants are favored, the denominator will be large and the numerator will be small, and therefore KEQ is a large number over a, no, I did that backwards, small number over a large number. We're going to get a small number and it will be less than 1. So you can be given a KEQ and an acid-base equilibrium, and from that you will need to determine who is the stronger of the two acids and who is the stronger of the two bases, who's the weaker of the two acids, who's the weaker of the two bases. I said something wrong there, but you know what I meant? Who's the stronger and who's the weaker of both respective acids and bases? Yes? Okay. Now, I wonder if I wrote this. Was I clever? No. So I'm actually going to write this down now. What do you notice about the stronger acid and the stronger base? Where are they? They are on the same side. They will always be on the same side, okay? So the stronger acid and base will always be on the same side. The weaker acid and base will always be on the same side, but they will also always be favored. And I know it doesn't make any sense, but there's an expression, the meek shall inherit the earth. Have you heard that? No, then this won't help you at all. So the meek shall inherit the earth, which is kind of like the people who are like sort of lower down will do well, blah, blah, blah. So the weaker is favored. Oh, it was in a song when I was a teenager, but you weren't teenagers when I was a teenager, so you don't know the song. It's okay. So weaker will always be favored because the stronger ones are always pushing away. You can think of it as a push and pull thing too. So if you've got two strong things pushing one direction, you're going to mainly go that direction, yes? If you've got two weak things, you're mainly not going to go that direction, yeah? So you'll end up hitting out the weak stuff. All right. let's try another one. We have H2C6H5O7 plus HSO3. Who are the products of the reactants? Uh-oh. These guys are both H and negative. H and negative, what are they? They are both amphiprotic. Oh! So who is going to act as the acid and who is going to act as the base? The stronger of the two is going to act as the acid and the weaker of the two is going to act as the base. Well, the weaker acid will act as the base. Yes, the stronger acid will act as the acid. Okay, so we look at our two Kas. We can get these off of the table. You can also just go to the table and look at their respective heights. You won't have that table on the AP exam, so you'll need to just look at the numbers and go, oh, look, Ka of, is that dihydrogen citrate, I think. Dihydrogen citrate is bigger than hydrogen sulfite. Yes? So if it is bigger, then who's the stronger acid? H2, C6, H5O7 minus is the stronger acid. It will act as the proton donor, which means our proton is going from here to here. So who are our products? This guy has lost a proton, so we have H, C6, H5, O7 minus, plus H2, SO3. What? 2 minus because it lost a proton. Yes, yes, thank you, thank you. There we go, 2 minus because it lost a proton. Very good. So that's great. We have now determined what the reaction is. So if you're given two amphiprotic substances, you can't just be like, okay, who, go and write my thing. You've got to compare. But then you have to do a second comparison, and we'll just rewrite this here. 7, 2 minus, plus H2O3. Who are our two acids in this equation? This is an acid here because it's giving a proton. And our acid in the reverse reaction is H2SO3. And now we have to compare those acid strengths. So do you see we're having to do two comparisons? First, to say which of these amphiprotic things will act as the acid and which will act as the base. And then we have to say which of my two acids in the equilibrium will be stronger. So H2SO3 has a greater Ka than the dihydrogen citrate ion. So H2SO3 is the stronger acid, which means that this one is the weaker acid. Are the products favored or are the reactants favored? I'm jumping a couple steps here. That's what you meant. That's what you were saying. That's what you said, right? Who's favored? The one on the left side. Did I tell you guys about that girl who got L and R tattooed on her hand? Yeah, I thought that was you guys who had told. Yeah, anyway, yeah. So we have our weaker acid over here. What does that tell us about the strengths of our bases? Who is this weaker base? HSO3 is the weaker base. And this will be the stronger base. And the weak ones are favored. What does that tell us? That means that the reverse reaction is favored, therefore the reactants are favored. So what could you say about KEQ for this overall reaction? KEQ is small, KEQ is less than 1. We probably work through that. Think of the two acids as pushing the reaction in one direction or the other. The stronger acid is better at pushing the reaction away from itself, therefore the side with the weaker acid will be favored, and also the same goes for the bases. Okie dokie. Do you guys want to try this one? Give it a go. Steps are all there if you need to follow them. Have you guys handed in all your CLC stuff? Yeah? Good. If you haven't, Ms. Deach, she's like almost 70 years old. She's going to have an aneurysm one of these days. Do you know how many student stuff she has to mark? Hundreds. She is marking stuff for like over 300 students because she's got like all of them. So if you have not handed it in, you need to do so now, because otherwise, like, you got to feel sorry for this lady. Like, nobody else has taken this on. Like, she's just dying under it. Okay. I can't imagine being 20 years older than I am right now and having like 300 students stuff to mark. I think I would just like call it quits. Well, there should only be a -1 on that there. Okay. The H2PO4? Yeah, it should be just 1 minus. There's a typo here. That should just be -1. -1. I think what happened is I knew there were a couple problems with this worksheet and I wanted to fix them, but then I needed to get it to the printer, so it never happened. Oh, hang on. You like that one, do you? The hexaaqualuminum ion? You did. It sounded good. So once you've done the comparison between your two reactants, then you say, well, this one is not acting as an acid, so I'm going to get rid of that. And I'm now no longer comparing it. I'm going to compare it with the other acid. And now I'm going to compare these two. I thought I changed this so we didn't have 3 in a row where the reactants were favored, but apparently not. So that makes me a little sad, but that's okay. I know my intent was to change it so we didn't have 3 in a row where the reactants were favored, but you know. Okay. Did you guys get the same as me? KEQ less than 1? Okay, awesome. Remember the side with the what acid and base will always be favored? Weaker. Oh, look, we're at the end. That's perfect. Huh. I have a review of solubility because probably you'll want that before next what? Tuesday. On Thursday, what do you have? You have the quiz. You know what sections you could review for the quiz on Thursday? 3.2, like everything, but if you want review for it, you can be like, okay, what am I doing in section 3.2? Where's my solutions? Oh, there we go, solubility. So it's like the HIJ, yeah? Solubility math problems, extra practice. Solubility math, extra practice through 2. Okay, so those are there for you. This I will put here, and then we'll move all the other things out of the way so you're not don't put anything to the back of the table, only from the front of the table. Well, I forgot how exhausting a day of teaching is. Man, I just want to go home and sleep. Same thing with coming to school, right? I hear you. I really, really hear you. I kind of broke it down for myself a little bit. I would do a little bit of like housework, and then I'd be like, okay, I had a deadline on the first week. I had to get your new file off the printers. So it's good to have a deadline hanging over my head because otherwise I wouldn't have done anything. Sure. I'm just going to grab a different pen because this one's dying. We will see. Okay, I'm going to promise you two. I promise you I am going home and I'm going to do some yoga. You check with me tomorrow and ask me if I did. I'm going to be accountable. Oh.